you, but I can see you at least.
You can see me. Okay. I think we are live now. So let's start this session. It's for me a great pleasure to introduce to all the audience Professor Orlando Rojas, a colleague and a friend for many years. Orlando is professor at the University of British Columbia, more recently in Canada, and he's also professor at Aalto University in Helsinki. Let me say that Orlando, I consider him as a world top scientist in the field of materials from renewable resources, including cellulose, lignin, proteins, and so on. Orlando started his career in Stockholm at KTH. Then he moved to North Carolina State University, so in the States, where he spent, I guess, 10 years or so. Then he came back again to Europe, to Aalto University in Helsinki, and more recently he moved again to the Americas, to Canada, to British Columbia, to Vancouver, where he was appointed as director of a center of excellence on bioproducts and biomaterials. That is a very important center of excellence that involves about 40 professors at the University of British Columbia. Orlando has received many prizes and awards. I should only mention a couple of them. The first one is the Anselm Payen Award, which is, let me say, the Nobel Prize for the guys that love cellulose, and Orlando was one of the recipients of this prize. He was also elected as fellow of the American Chemical Society and the Finnish Academy of Sciences, and he was recipient of the TAPI Nanotechnology Award. Just to finish, during his career, Orlando has followed, imagine, 57 PhD students, which is a enormous amount of training of young people, and he published more than 400 papers, peer-reviewed papers, and is certainly one of the authors with bigger impact on the scientific community on cellulose field. So for me, it's really a great pleasure, Orlando, to have you among us and to talk about a topic where you are extremely motivated and you have made big contributions in the last few years. So you are going to talk exactly about the paradox of papermaking, considering the emerging nano and microcelluloses. So, Orlando, the floor is yours. You have more or less 30 minutes.
Thank you so much. It is a great pleasure to join you, and this is a great opportunity to talk a little bit about papermaking and also the science of papermaking that I still love and I really feel very excited about. And to start, I would like to very briefly comment on the circular bioeconomy, the way we see. And we need to, I think, be very conscious about the fact that with the sustainable use of the forest, we are fixing atmospheric CO2. And this you can see in the blue and green arrows in this circle of time. So we go from year 0 to 440 years in the full circle. And this is very nice because what we're looking here is into fixing carbon for long-term storage. And what a better example for carbon storage than the construction. And especially if in the construction materials, we can recycle wood that is being used. And these are the brownish arrows that you see in the circle. And this is very well represented by today's beautiful buildings. And I put here this one in UBC, in University of British Columbia in Vancouver, very close to where I'm talking to you today. Is a 18-floor building built from wood. So it's a beautiful example of what we can do. And this wood can be recycled, and I think there is an important incentive for us to do this because of this circularity that we all envision. And that also can go to furniture and fittings, that is materials that then in the end of life can still be reutilized. But in the paperboard production and textiles, we have the similar situation, even though the time cycle is smaller, but we can recycle. And if you compare the percent recyclability of paper compared, for instance, with plastics, there is a huge difference. So these yellow inner circles represent the production of paper and recycling paper that at the end of life, when the fibers cannot be finally utilized to making more paper, still can be used for energy to produce pellets or to produce micro nanocelluloses. So this is the topic today. I will talk about paper making and also in the context of the use of nanocelluloses. And I put as a title to my talk, the paradox of paper making. And my motivation was that in 2004, in one of the, at the time, RIADISIP consortia, nowadays CIADISIP, the Hispano-Iberian community met again in 2004, and I gave a presentation about how paper making really is a miracle. And there are a number of paradoxes that I want to comment in the later part of my presentation. But already in paper making, I need to say, we are already talking about nanotechnology. So without knowingly, when we think about nanocelluloses, microcelluloses, this is already there since early in times when we were doing paper making, when we were using different chemistries in the wet end of the process. So as an example here, you can guess this is a hardwood sample dispersed in water. We can observe the fibers and the vessel elements. Probably we can think on eucalyptus fibers. And there in the red line, we have the dimension, 1 millimeter. And that would be a vessel element that where we can zoom in. And this is an actual drawing of my colleague Martin Huby that at that time we wrote a number of papers on the topic just to get the education started, to make students sensitive about the fact that in paper making we have already nanocelluloses. So if we go to the vessel element, then we can find a different landscape where we have the wood component, the vessel elements there on the bottom left. But also we can observe a number of other particles that are typical in the wet end chemistry: kaolin, bentonites, titanium dioxide, polyacrylamides, and others. But we can go further in, and if we zoom in, then we're going to find now the nanoscale materials that I start to reveal, for instance, the starch, cationic starch, or colloidal silica. So my point here is already we're using here nanotechnologies very early on, not only nanocelluloses, but also in inorganic particles. So we're time to nowadays, we are now still looking into the paper making pretty much similar process than in the 1800s. And at the time when we wrote this paper about the paradox of paper making, we actually listed 7 paradoxes. And today I will only comment in the context of nanocellulose 4 of those paradoxes. The first paradox is divide to combine. The second one, add water to then take it water away. The third one is swelling water and then dehydrate and shrink. And then finally, the last paradox is to use waterborne treatments to make paper water resistant. So it's a beautiful dyslexia between what we do in paper making, adding water, for instance, and taking water away. So it's just an example. So let's go into this discussion with these 4 paradoxes, and I will put this in the context of nano microcelluloses. So the first paradox, divide to combine. Here we have wood fibers that we disperse, and then we put back together into paper. That's what you see on the far right. It's a beautiful example of engineering. We engineer the fibers and we try to take all the attributes of fibers, the intelligence of fibers, the functionality of fibers, making 2-dimensional layer structures that we know as paper. And if we look at the wood, or trees, of course, we want to use as much of it in making not only paper, but other materials. So nowadays, of course, we are discussing, and in this conference, we are discussing nanocelluloses in the form of cellulose nanofibrils and cellulose nanocrystals on the far left, but also other emerging nano micro materials, including lignin particles, like the ones that you see on the top right, or tannin particles, for instance, from bark. So this is a excellent time for us to do very basic research, but also connecting with the application and the impact. So recently, we published this paper in Nature that relates to a perspective of the hierarchical structure of fibers and nanocelluloses. And as you can visualize here, we start with the fibers on the top left. And as we process the fibers in deconstruction, we add energy. And of course, that adds to the cost, but also adds to the process challenge. But this is known to paper makers. We know how to defibrate, convert fibers into fibrillary structures. And that's what we do here in the refining and deconstruction process. Now, together with this, we're looking also at finer materials that go to the nanoscale. The price, of course, and the value will also increase, and also we will add performance. And this is what the business proposition is for nano and microcelluloses, as well as lignocellulose and the particles that I showed, like lignin and tannins. And this is really something that is becoming a reality. And here I put just a strategy of Finland, for instance, in this direction. We have the value of production in the vertical axis on the right plot versus time, and we see the current forest products in red, and how with time we're going to see more new value-added products that we will comment at the end that can really make a major impact in the GDP of the nation, or the total exports, or the number of jobs. That applies to Finland in these figures, but can apply to any country like Canada or Portugal, or any of the countries participating in this conference. So one prime examples of these nanomaterials, of course, is cellulose nanofibrils, but I want to add an L in front of that to refer to lignocellulose nanofibrils. There is a huge opportunity in this area. We cannot dismiss the contribution of lignin in this effect. And here I want to just refer to some recent work. We have been working on this since a long time ago, but the most recent one points it to the fact that if we take fibers, in the case that I'm discussing now, is actually all corrugated board. We took all corrugated board and we fibrillated the material. Imagine this as a recycled paper that we are fibrillating to produce nanocelluloses. And these are the ones that you see on the left, far left. We can produce coarse fibrils, and we can make them by refining further medium or to even the finest fibrils by also using homogenization. So for the coarse fibrils, that's what you see here in the AFM image. We see the size of the material, and since we have lignin, an observation is that the residual lignin in those fibrils have a molecular weight of about 10,000. It's an apparent or relative molecular weight, about 15% of lignin. If we go to the medium-sized fibrils from the same source, you observe that the molecular weight of the lignin that remains on the fibrils is higher, and also the concentration of lignin is higher. And then finally, for the finest, where we find the smallest fibrils in the system, then we have a further increase in the residual lignin molecular weight, and also the amount of lignin, in this case, 25%. The gray images show the plain view of the fibrils, and then the cross-section of films that are made from these fibrils. Now, what is nice about these fibrils from the point of view of paper making and the theories of light scattering that are very common to paper makers is the fact that if we take those fibrils, we can make paper materials where we can control light scattering and opacity. In this particular case that I'm showing here, I'm talking about bleached fibrils, so it's not the same case than before. These are whitish fibrils, and therefore these are from bleached fibers, but the same conclusions apply. Here, what you can see is papers or films with the same basis weight can be put together with a very good control on the opacity. Again, minding that we're talking about the same basis weight. So the bottom green circle is the same material, but using the coarse fibrils, where you see the very high opacity, very high lighting. The green circle on the top right corresponds to the same film, but produced from the finest fibrils with the same basis weight, a completely transparent material. So it's a beautiful example of what can be done if we engineer the fiber morphology combined with, in the previous case, with the lignin presence that can be quite important. So let me talk a little this and how this can be monetized. I put here very recent work with our colleagues in North Carolina, where we took related lignocellulosic nanofibrils and we use them to reinforce paper or to typical writing type of papers, but also to reinforce tissue paper. And the main observation that was obtained is that really we can replace a great deal of fibers and increase the strength with actually some savings in fiber cost. So on the right, I show what is the cost, the manufacturing cost of the lignocellulose nanofibrils for different sources, different fiber sources to produce those nanofibrils. And you notice that the far right bar represents fibrils that are produced from the ink pulp that is produced on site. So relatively low price. And those fibrils can be added in tissue paper making to actually reduce the price. And there are already examples at industrial scales where such addition can really represent major savings in the production. And it's not only the paper properties, it's also the coating properties of those papers. So this is a very complicated slide, but what I want to say here is that coating lignocellulose nanofibrils or adding lignocellulose nanofibrils at 2-3 grams per square meter on paper, one can achieve really an increase in the water resistance, higher contact angle, better print density, rubbing resistance, ink transfer, and many other properties. And interestingly, in this particular case, what we're trying to show, or what we're showing in the red lines, is that the nanocellulose fibrils compares very well with the fibrils that are lignin-free. So there is no major difference as far as the. So that's enough of nanocellulose. Let me talk very briefly about the case of lignin, and some of you maybe are already familiar with this work that we published several years back. But essentially, we take lignin, we solubilize in appropriate solvent and produce the lignin particles. And for that, we use this aerosol system. So here, there is no pH shift. Here we don't use solvents. We just take the lignin solution. It can be the black liquor, as you see in the center, and we heat up that liquor, and then by using a air stream, we let the droplets to solidify into particles. And these are lignin nanoparticles, microparticles that you see on the far right. A beautiful aspect of deconstruction and putting things back together, that will be the paradox one that we are talking, is that if you take those lignin particles and you mix them with the nanocelluloses that we just saw, we can get a super interesting network that is combining the two original components in the tree, lignin and fibers, in this case, nanofibers. And that has allowed us to do things like microfluidic channels, 3D printing, or creating self-standing films and membranes like the ones that you see on the right that can be very good for their antioxidant properties, UV protection or shielding, as well as enzyme or protein rejection, so anti-fouling properties. Further example of these systems based on lignin together with nanocellulose is that such films can be made super hydrophobic, as you can see here, with a very high contact angle, higher than 150 degrees, and a tilt angle of 5 degrees. Very interesting materials, again, for protection, for coating, and many applications. So this is perhaps 2 or 3 examples of paradox 1. Paper makers dividing materials to putting them later together to engineer given functions and properties. Let me now the paradox number 2 of paper makers, but placed in the context of micro and nanocelluloses and nanoparticles like the ones that I just introduced. So here is a second paradox. Paper makers add water to then take it away. So that sounds like a stretch, but that's what we do every day in very large volumes. So we take fibers, we make it wet, and then we in a dry state. And of course, you may wonder why we do that. Of course, the answer is very clear, but for paper makers, but we need to maybe teach our students that this is the idea. We put a lot of water in paper making processes. Typically, we use 200 mass units of water per every unit of fiber. We are an industry that is very water intensive, and recirculation of water and closing circuits is super important. So the question is, why such high dilution? And the answer is very clear, is the fact that fibers tend to entangle very quickly. There is a number called the crowding number discussed by Mason and later by Dick Herrickes here in UBC that talks about fiber forming flux in a flowing suspension, and that really prevents a smooth running of the fibers to make paper. So we need to dilute. And that brings technology that has been around since the 1970s, and that will be foam forming or foam laying. In foam forming, what we do is we take the fibers, suspend them in water, but we inject air, and that's what you see on the bottom right. Essentially, we replace 70% of water with air in the form of bubbles, and then the bubbles suspend the fibers, and then in the forming board produce the fiber web that then is dry, and then we have a paper-like material. So how can we think about this foam forming process that actually is receiving a lot of attention nowadays? And this is thanks to all the technologies that have been advanced by VTT in Finland. But minding that this is a technology that came from UK, it was also very heavily researched in UBC and many other places. In foam forming, what we do is we take a complex fluid, liquid foams. And liquid foams, if we make them drier, if we add more air, then we can get the so-called dry foams. And foams are very special complex fluids because first, they are shear thinning, the viscosity depends on the air content, and the bubbles behave as a carrier for particles, and by themselves, they can be considered as the particles. Now, one thing that we observe in our work with foam forming in the presence of nanocellulose is what I show in the blue photo on the right, is the fact that nanocellulose really increases the stability of foams, and that can be useful in some applications, including foam forming. So here again, the possibility of having very small fibers between the bubbles is quite interesting. Let me expand a little bit more about foam forming from the context of paper making to discuss the paradox number 2. First, foam forming allows us to move from a layer structure that we know paper is. So on the top left, we have the layer structure of fibers in paper. In the bottom, with foam forming, what we observe is that the structure becomes more felted. That means that fibers will be across the plane of the fibers. And that means, or the layer structure, that means that then here we have new properties in papers that are not typical for the layer structures that we know of. The other component with foam forming that I think is most important is the formation. Formation, as you may know, can be measured by the specific formation index. It's pretty much the square root of the grammage. And that means that the lower the value, the better the formation. That's how we read this plot on the right. So it's a better distribution of the fibers across the plane. And what we have here is a reference on the far left in triangles. And then we have papers that were produced with water, the blue circles, and those produced by foam laying or foam forming in orange. And for this purpose, we compare different surfactants that were used as foaming agents. So anionic, cationic, non-ionic, and amphoteric surfactants. These are the different lines. And at this point, it doesn't matter the details. The point is that you observe that the foam-forming papers have a lower specific formation. That means better formation. And this is very important for foam forming, meaning that we can afford to use longer aspect ratio fibers to produce better formation, better paper quality. And of course, that can translate into many other properties. One of these is the enhanced water removal. So in this plot on the left, we have the residual water at the end of the forming board versus the density. And again, here, the details don't matter, but you can see the data for the wet lay paper, typical paper making process. That would be the blue data for both mechanical fibers on the left and chemical fibers, and also for different type of systems. In the bottom, in orange, those produced by foam forming. And what you see here is that all the data for foam form or foam laying paper gives lower residual water at the end of the formation unit. That means that we need to evaporate much less water in going to the press. So in general, we're talking here about foam forming to improve out-of-plane organization. That can be very good for producing higher compression resistance. We enhance water removal before the press and, of course, before the drying section. That means energy consumption is reduced. And then we can also achieve more porous and uniform paper, as well as typical paper or even foams. So this is a major evolution where fibers as well as nanocelluloses can take part. An example is, for instance, using foam forming to make acoustic panels, insulation materials, and others by using this type of technologies. To put an eye, so I'm talking here now about something that we did recently, and we use this as a concept to explain to the community how fibers can be used as well as nanotechnologies to make next generation materials beyond the traditional paper materials. And again, this is an integration of paradox 1 and 2. We take wood components, we take nanocelluloses, nanolignins, nano fibers themselves, and then we put them back together by foam forming into this that you see on the right. And of course, this is very timely now during this pandemic. And a process that is exemplified here on the left relates to the production of masks using 3D printed by suction. We just deposit the formulation to produce the mask. And interestingly here, depending on the fiber type, we can achieve a filtration efficiency that is competitive with those of surgical masks that you can see on the right diagram. So beautiful opportunity where paper products can be used if we think about different technologies, including foam forming and nanotechnologies. Number 3, this is another dichotomy in paper makers' mind. We swell fibers and fibrils in water, and then we dehydrate and shrink the fibers. Why we do that? Why we put water and let the fibers swell, and then we shrink the fibers? One of the reasons is that in a state of swollen structures, the tensile properties of a network can be improved. And this is in part because the fibers become more flexible, we have a higher bonded area, but as a trade, of course, then we need to remove more water. But this is important, and in foam forming already, we saw an opportunity here to reduce the amount of water. But the main point here is that the microporosity that is produced in such materials that are swollen means very small capillaries in the paper network that translates to very huge forces, 4 to 200 megapascals. How this can be translated to nanotechnologies. Of course, papermaking is an example, right? So here we have a lot of nanotechnology already. But let me put a recent exercise that we published last year, where we cellulose nanocrystals, and we let them to be confined in a suspension between 2 glass slides. That's what you see on the left. And then by letting the system to dry up, it will self-assemble the crystals into these linear structures that you see at the interface on the right. So this really is a reminiscent of the gecko feet, where we have structures that are lamellar or are forming stripes like the ones that you see again in the image, and in fact a picture, a microscope picture on the far right. So this is very important because that allows us to produce super adhesives using cellulose nanomaterials. And an exemplification of this is shown in this video where my student, Luis Greca, is standing on a crossboard that is glued by using cellulose nanocrystals in water. Few droplets are glued at the both ends, left and right, and then it can support 72 kilograms. It can also support my weight, 9 kilograms. And that will be in the shear mode. But if we do normal detachment of the components, then it's very easy to detach. That means that we have an isotropic super adhesive. And this adhesive actually is very competitive against all known adhesives that are based on synthetic products. So the example on the right on the picture is the same that I showed earlier. In the case of 2 glasses light, is 9 megapascal shear strength. And that strength is shown here in this map for the adhesion versus shear strength in the green bubble or the green cloud. And that's this work based on water mixed with cellulose nanocrystals. Few droplets will do the job compared to microfabricated adhesives, compared to commercial structural adhesives that are super expensive. Example of the power of separating components and mixing them together, but especially letting them to swell and then to shrink, is this idea of a universal binder. And in this particular case, we're talking about supraparticle systems. The particles that you see on the top left, silica, iron oxide, lignin particles, clay, pollen, titanium dioxide, are shown also in the bottom. They are mixed with cellulose nanofibrils, and then what we found is a very interesting correlation between the yield point or the strength of the structure versus the ratio of the particles versus the addition of the fibrils. And those materials that are produced are super strong, and also are or enable technologies such as 3D printing, where we can put things together and have structures that are pretty strong. Again, mixing different particles with cellulose nanofibrils as a binder that first swells in water and then shrinks. The final example in paradox tree about these interactions with water is the creation of textiles. And of course, this is very typical nowadays in wood industries, where in Finland, for instance, there is a lot of discussions about investing in new generations wood dissolving ionic liquids to produce next generation textiles. This is shown here also in the case of dry spinning of nanocellulose, again, translating large scale materials to nanomaterials, nanocellulose together with, in this particular case, alginate. And also, of course, in other processes where we mix lignin to nano, and we use the same principle that was explained in this paradox to remove water, let the system shrink, and in this particular case, to create filaments that are super interesting for advanced textiles. Okay, I have only minutes left, so I will take the last bit of this conversation to talk about paradox number 4, and that relates to using water-based treatments to develop water resistance, another paper-making sort of paradox. And the typical example for paper makers is what you see in the bottom is, for instance, rosin sizing of paper in the older times. But nowadays, in the context of nanocellulose, we can talk about, for instance, co-grinding or homogenizing fibers, cellulosic fibers with tannins, and letting the tannins to interact with the fibers to produce nanocellulose, and from this to produce papers, and those papers become water resistant. So a beautiful example of using two water-based components that, when placed together, develop water resistance. And this is similar to the example of rosin sizing in typical paper products. The other example that we have worked on is mixing cellulose nanofibrils with chitosan. Both are hydrophilic, both absorb water, but when you mix the two and you create a paper material with chitosan and nanocellulose, then you can get first very high transparency, And second, you develop water resistance. That water resistance, of course, can tune to produce, for instance, papers and nano papers. So here I'm talking about both macroscopic fibers in paper and also nano papers using nanocellulose that can be very easily modified to produce super hydrophobization. And there are many techniques to doing this, and I'm sure many of those. But an example here is the UV coupling that we have presented as a way to actualize paper in such a way that we can make the areas of that are hydrophobic and hydrophilic to be together in any design that we wish by using different photomasks, as the example that you see here on the right. Some areas are wetted by water in green, some areas are not wetted. And this is important. And I just put as an example here, the next generation paper electronics. This is already an activity that is typical in many advanced paper products. But in this particular case, in a Horizon 2020 project with the partners that you read in the bottom, we're looking into locally hydrophobizing paper and creating tracks so that we can produce paper platforms where we can print batteries, antennas for transmitting or communicating data, electrochromic displays, and also sensors. So you can go to the website to find more information, but it's the beauty of, again, mixing the old technology with nanotechnologies to create materials that are quite advanced, and in this particular case, to make intelligent paper products. So this is all. I wanted to bring the old talk of the 4 paradoxes that I gave in 2004 in Cordoba. That was in Cordoba, with today's nanoscale materials and how micro and nanocellulose fit this proposition for the next generation materials. And I want to highlight that what we need here is deeper knowledge in wet end chemistry, all wet end chemistry. So I really admire very much the principle of paper makers that we know by tradition in our schools, that we need to revisit and relaunch so that we really advance the materials of the future, like those that you see on the top right. So this is all we want, to harness the natural properties of lignocellulose to create new sustainable materials. My acknowledgement goes to UBC in Canada and Aalto University in Finland, the 2 flagships that we have there, the Bioprocess Institute and FinCERES. Today we launched the Border Alliance, a major effort between the 2 institutions, NSERC in Canada, and the ERC Advanced Grant that also funded some of this research. Thank you so much. It was a pleasure to share with you my thoughts.
Thank you very much. Thank you very much, Orlando, for your fantastic, as usual, presentation based on the 4 paper-making paradoxes and how it inspired new materials that will certainly make a revolution in the next few years in our industry. The first general question, I'm waiting for common questions from the audience, and probably the first general question, and looking at how your 4 paradoxes have led to new materials, new fantastic materials. How do you see the future paper mills, and the future is tomorrow, I should say, in 10 years, the future paper mills regarding and taking into consideration all the advances that are taking place nowadays? How do you see the paper mills?
Definitely, and you know better than me all of this, because in your company, I think Navigator, there are beautiful examples of what you are thinking for the future. So my general comment is that we're looking into using every molecule in the tree, and in the process to have a fully integrated process. That means using fibers to produce paper, but together with that, using lignin, at least those that, for instance, are excessive, or if we have a bottleneck in the boiler section, for instance, any excess of lignin to produce lignin materials. Lignin has become super hot topic nowadays, and you know there are many investments now by industry in the area of lignin. So lignin, then bark utilization, beautiful examples exist. And I think we had to think beyond burning bark as an energy source. Many different business propositions around bark. So my general comment is use paper products as the large volume business, but to develop satellite processes that are integrated, like the ones that I just mentioned. And this is already taking place in companies as yours, but many others around us. We're thinking about textile investments, also biomedical departments in some pulp and paper companies that are investing in nanocellulose. And we have talked in the past also, for instance, in using some of the biological streams to produce bacterial cellulose and other materials. So it's an amazing opportunity if we think about the biorefineries of the future, and I think this is already around the corner.
Excellent. One general question for our audience. When you compare nanocellulose or microcellulose, but nanocellulose, and when you compare with cellulose fibers, paper-making fibers, at the end of the day, is cellulose in both cases. How do you explain these fantastic differences and the fantastic materials that you produce from the point of view of chemistry is exactly the same, but something is different? How do you explain it?
Yeah, it's the beauty of the nanotechnologies, essentially reducing surface area. We then open up new properties that are not typical in macro scale or colloidal systems. So that's the power of nanotechnology, exactly that. And the first nanotechnologies that we know from papermaking is a microparticle system. That's an example of a nanotechnology. But earlier, when we thought about highly fibrillated samples, we have fibrils and fines. There we have a lot of opportunities for fine engineering. This is nanotechnology. So those properties have to do essentially with the development of higher surface area, better bonding, and some of the examples that I put in my talk relates to that possibility. Generate higher surface area for better bonding, better properties, and that involves light scattering as well as strength, as the examples that we explained.
Okay, many questions from our audience. Unfortunately, the time is running. But one question that is in some way related to one of my previous question, but how do you see the industrial production of these materials in the next decade? And I mean, in not only nanocellulose-based materials, but on also these lignin-based materials, tannin-based materials, and so on. How do you see the industrial production?
Yeah, we don't need to wait. This is not the next decade. It's already around. So in Canada, there are many investments. For some reason, very focused on cellulose nanocrystals and other called biofilaments that are fibrillated celluloses. Then if we shift to Europe or the US, there are many examples where nanocelluloses are being produced. So really, this is already here. And internally, many companies, they are already using nanocelluloses. So this is not something that will come. It's already around. Of course, we can think about the price and the cost, but I can tell you, based on what I showed earlier, that the cost is actually quite competitive. And I have an example from a company that is actually reducing the production cost quite a bit every year because they add micro nanocelluloses to the paper making process to replace fibers with very tiny amounts of nanocelluloses. So there is actually a business proposition here. This is here to stay. And if you want, maybe you can look at this paper in Nature that we put together. And I think there you will become convinced that fibrillated materials based on cellulose are really the materials of the future.
Okay, I think we have time for one last question. This is a very specific question, but that get a couple of votes from our audience related to lignin. Did you separate lignin from black liquor for the preparation of lignin nanoparticles, or these were produced directly without any separation and purification process?
So whatever comes in, comes out. Meaning if we have a lignin mixture with salts or other components, hemicelluloses and carbohydrates, that will go to the particle. So the particle will be generated regardless. It depends on the composition of the initial solution. If it is a black liquor, what we get is whatever is in the black liquor. It's a 100% yield process, right? And that opens the opportunity to really fine-tune the lignin particles. If they are going to be used in crop protection or as a bioactive component in fertilization, then we can change the composition of the lignin solution. Further, if we use lignin solutions coming from the organosulf process or the sulfite process or the craft process, you can imagine that the particles will be completely different, meaning some will be more hydrophobic, some will be more hydrophilic. A beautiful example of nano microtechnologies where we can fine-tune the properties of the material. And finally, if we do fractionation in a lignin-centered biorefinery where we separate lignin by molecular weight and solubility, you can imagine the properties of the particles that are produced will be different depending on the lignin source. Beautiful opportunity for us in the biorefinery concept to produce next generation micro and nanoparticle systems.
Okay, Orlando, time ran very, very fast, and we need to move to the next section. It was really a great pleasure to have you here with this inspiring talk, and hope that I cannot say that we can meet on the coffee break, but certainly we will meet soon, and certainly we will have the opportunity to follow this discussion. Thank you again, Orlando. Bye-bye.
My pleasure. I give the floor. It was great to see you.
Thank you. I give the floor to Paulo Barata for the papermaking session. Thank you.